Okay, that's why we are going to cover define and calculate binding energy, sketch the graph of binding energy per nucleon, apply binding energy to nuclear reaction, introducing Q value to tell us whether the reaction is possible, application to fission and fusion. Okay, that's the syllabus. We won't go over with them. The key formula is this one. Right? Where if the mass disappear, it appears as energy. E is energy. This is the mass in kilogram. This is the speed of light. This is Einstein's relation. Then we define atomic mass unit as 1/12 the mass of an atom of carbon-12. Okay, and we say the atomic mass unit is actually the average mass of a nucleon in carbon-12. Okay, we stop here. Data and atomic mass unit. Normally, when you calculate, we cannot round it off. Right? It's convenient to use atomic mass unit rather than kilogram because every time you have to use minus 31. Atomic mass unit is a convenient way to measure the mass of atoms, nucleus, protons, and neutrons. Is the average mass of proton and neutron in C12. Normally, you need to keep the number of significant figure used. Cannot round it off. Example, if you round it off to 3 significant figure, proton and neutron will have the same mass. Okay. Okay. One atomic mass unit is mass equals 931 energy. That's a conversion equivalent. If you cannot get the answer, explain how. Okay, we use Einstein's relation. One atomic mass unit from data sheet, we get this value. And we use E equals mc squared. That's the mass. That's the speed of light. Calculate out. You get in joule. Then this one you need to remember. Right? So one atomic mass unit, that's the energy. Divide by that. Right? We get 934 mega electron volt instead of 931. Any idea why we cannot get 931? Any suggestion?
We don't get
931. We get 934. Any idea?
not sure.
Basically, we use approximation. Right? Elementary charge is 1.6. Right? It should be that one. Should be higher. Right? Slightly higher.
Or slightly higher.
Then atomic mass unit. Instead of that, slightly higher also. Right? Atomic mass unit. This one value will be higher lah. This value will be higher a bit lah. This value will be higher also a bit only lah. Then speed of light, it will affect lah. Because this is we use 3 instead of 2.99 instead of this value lah. Okay, that's the reason why we cannot get 931 lah. Get 934. Okay, this is for info. Info is just read for info, that's all. Electrostatic and gravitational force between nucleons. Nucleons are protons and neutrons. Protons are positively charged, and so their force protons are positively charged, so their force. Hey, what is happening here? small separation, electrostatic repulsion. Okay, I think there's something wrong with this. For small separation, electrostatic repulsion, right? When you bring proton to proton together, there will be repulsion. It becomes greater and greater as it comes closer and closer. Right? As it becomes closer and closer, it's quite large. This force can be quite large when its separation is very small. The other force acting on proton is gravitational force or force of gravity. But this is very weak because the mass of proton is very small. Right? Two protons in the nucleus are about 0.10 to the power minus 15 meter apart, so that the force of gravity between the two protons will be, you can calculate out using E, F equals to G m1 m2 over r square. You can calculate that this value of attraction, that's the gravitational attraction, but the electrostatic attraction is 230. You can use a Coulomb's law to calculate, right? And this is a repulsive force, 230. This means that the force of gravity is nowhere near large enough to hold the proton together in the nucleus. So proton and proton, repulsive force. Gravitational force is too small to hold them together. Right? That's the gravitational attraction. That's the repulsive force. So you can see that, right? The repulsive force is greater by 10 to the power 36 times. Neutrons have a force of gravity as attraction, but again, it's extremely weak. So we cannot explain why the nucleus is stable. Right? By gravitational force attraction is very small. Neutrons have no electrostatic force because this is neutral. Proton repel proton with electrostatic force. The electrostatic repulsive force between proton and proton are long range. Right? That means they act over long distance. Most nuclei are stable. For example, helium nucleus is stable. It has two proton and two neutron. What hold them together? Right? That's the electrostatic force. This one treat as the only thing you need to remember is nuclear force is attractive force as well. No need to go into too much detail like what I do here. Since nucleus is stable, there must be attractive force between the nucleons. This nuclear force must be stronger than the repulsive force between protons. Neutron force or nuclear force is strong, attractive force, very short range, about radius of the nucleus, right? About the distance of very short distance, about the size of the nucleus there, 10 to the power minus 15. These forces become negligible as separation of more than a few nucleon diameters exists between nucleons. That means proton and proton, besides they have electrostatic repulsive force, they also have nuclear force when in the nucleus. Between proton and neutron also got attractive nuclear force. Because between neutron and neutron, there's also attractive force. Right? Exists between nucleons, holding the neutrons and protons together to form a stable nucleus. These forces are independent of the nature of nucleus. It doesn't matter whether it is proton and proton or proton and neutron or neutron and neutron. Right? That's roughly the diagram. Right? This is a nuclear force, attractive. This is electrostatic force. So you cannot compress it too much. The repulsive force will take over. So it is about, if you take that as a nucleus, that is about twice the nucleus diameter, it will become zero only. Just for info only, don't go to detail. Right? At large distance greater than twice the diameter of the nucleus, the attractive force turns out to be the repulsive force. Repulsive force will take over long distance. This ensures that the nucleon remain as a separate particles, not as a discontinuous mass. Okay, this one, binding energy. The electrostatic force and nuclear force together determine whether the nucleus is stable. Right? These two forces, electrostatic force, repulsive force, nuclear force, attractive force, determine whether the nucleus is stable. An unstable nucleus decays to a stable nucleus, right? Giving alpha, beta, or gamma rays. Okay, if you have a positive charge and a negative charge, there's attractive force. So energy is required to separate them because there's attractive force. Where nuclear force is present, there must be energy required to separate the nucleons. An object on the surface of the Earth requires energy to lift it up as it's extracted to the Earth. Right? Same as an object at the surface of the Earth, you need to put energy in to lift it up because there's an attractive force between the Earth and the object. So remember that binding energy of nucleus is the minimum energy required to completely separate the nucleons of a nucleus. Right? The term completely must be there. Or energy released when individual nucleons come together from infinity to form the nucleus. The larger the binding energy, the greater the attractive nuclear force. Likewise, binding energy is large if the attractive force is large. Right? In a uniform gravitational field, the potential energy is PE mgh. If PE is large, if the height is above the surface is large, or the mass or the object or the weight of the object is large. Right? So potential energy is large if the height is large or the weight or the mass is large. Okay, mass of nucleus. This is the mass of nucleons that make up the nucleus. This is the nucleus. Right? The mass of proton, mass of neutron. Mass of nucleus is found to be less than the sum of the masses of the constituent proton and neutron. Right? So that is your X is the element. There's A is the mass number. Z is the proton number. For nuclide, neutron number is A minus Z. That's your AS work. So the total mass, right? This is the total mass. Total mass of neutron plus total mass of proton is greater than the mass of nucleus. Mass defect. Right? So you compare the mass of nucleus and total mass of proton and neutron that make up the nucleus. You can see there's a difference in mass. We call that mass defect. When we compare the mass of helium nucleus and the total mass of the individual nucleons, we find that there's a mass difference. There's a difference in mass. We call that a defect. Right? We call that different a mass defect. So total mass of individual nucleons greater than mass of nucleus. The mass defect or mass excess is the difference in mass between the total mass of nucleons in the nucleus when infinitely separated or completely separated and the nucleus. Right? That's our mathematical representation. That's a change in mass or the mass that's converted to energy when the nucleus is formed from the nucleons. Right? So that's the total mass of nucleons. This is the mass of nucleus. Binding energy, sometimes called Q value, can be calculated using Einstein's relation. Right? Delta M is in kilogram. C is the speed of light. The difference in mass, right, delta M, appears as energy released when the nucleus is formed from its constituent nucleons. Right? When the nucleon come together to form a nucleus, energy is released. Right? We can use the mass equivalent of energy. Binding energy per nucleon is defined as the total energy needed to completely separate all the nucleons in the nucleus divided by the number of nucleons in the nucleus. Right? So it's basically binding energy divided by number of nucleons, A. A is the mass number. This quantity allows us to compare the stability of different nuclei. Okay, let's calculate as an example using the data from data sheet. Data sheet just now given you mass of helium is given. Right? This is the mass of nucleus. Mass defect of helium, binding energy per nucleon. How do we calculate that? Right? There's the usually electron doesn't come in because we are involved in nucleus. Right? There's mass of proton, there's the mass of neutron. So helium is made up of 2 proton, 2 neutron. So add them up. Whereas the mass of nucleus, as is given earlier, so we subtract mass defect, this one, subtract that. So that mass that disappear become the binding energy. Okay, there's a atomic mass unit, that's 931. So it's 28.4 mega electron volt. Right? One atomic mass unit is 931 mega electron volt. Per nucleon is 28.4 divided by 4. That's how we calculate. We get 7.1 mega electron volt. Any comment? Anything not clear?
Okay.
Helium nucleus have a binding energy per nucleon of 7.1 mega electron volt, thus very stable. And let's just compare this for info, just for your information only. No need to study if you don't want to. Right? Ionization energy is about 13.6. Binding energy, when the nucleons come together to form the nucleus, you can see is mega electron volt. Right? Binding energy is about 2000 times greater than ionization energy. Nuclear reaction, driving force is a loss of mass. Chemical reaction, bond making, bond breaking, bond making. Nuclear reaction, mass and energy is conserved. Chemical reaction, conservation of mass. Right? So the energy that's released is about 10 mega electron volt. This one is about 10 electron volt. Proton that's produced is gamma ray. For chemical reaction, it's ultraviolet photon. Similarly, we can calculate the binding energy per nucleon for all the nucleus and plot a graph of binding energy per nucleon against nucleon number. The smaller the binding energy per nucleon, the easier it is to separate a nucleus from its constituent nucleons. A stable nucleus is one which has a very low probability of decay. Less stable nucleus are more likely to disintegrate. A useful measure of stability is the binding energy per nucleon. Right? Exam won't give you the actual one. They give you a smooth curve lah. Okay, this one is hydrogen 2. Right? It doesn't go to zero actually. It doesn't go to zero. Right? Deuterium will be here. Okay, let's look at that. So the largest one is uranium-238. Binding energy per nucleon against nucleon number, page 253. Binding energy value rises rapidly with increasing mass number. A rises very rapidly, you can see from here. For light nuclei, and starts to level off about A equals 15. A equals 15 is about here. About this part, it starts to level off to about 8. For all atoms except those lighter than carbon, right? Carbon is here, lighter than carbon. It's less than 8.0 mega electron volt for those that are lighter than carbon. Binding energy per neutron is 8.8 for iron, which is 60. Right? This is the largest one. The most stable with the largest binding energy. The greater the binding energy per nucleon, the greater the work that must be done to remove the nucleon. EA decreases for nuclei on either side of right? There's iron. So this side it decreases. This side it also decreases. The less the binding energy per nucleon, the easier it is to separate the nucleus into its individual nucleons. Right? Lower binding energy, easier to separate the nucleons from the nucleus. So helium, that's helium. Right? Has a large binding energy. So for heavier nucleus, we tend to go fission now. When heavy nucleus splits into two lighter ones, so the binding energy per nucleon increases with release of neutron. It's called fission. Energy is released in fission, or the smaller one combined together to form a larger one. So that's the energy release. Fusion energy is released when two lighter nuclides, right, from here, fuse to produce heavier one. And then this part, for those that are in between, will be nuclear reaction. That example will be gold. Geiger-Marsden experiment, scattering experiment. Sending alpha particles from radioactive decay towards gold nuclei was the first step to learn about atomic structure. The next step, what happens if we send an alpha particle into the nucleus of an atom? We need to accelerate the charged particle to higher kinetic energy. Okay, we can send deuterium and tritium together, and then energy is released when helium and a neutron is produced. Nuclear reaction, artificial radioactivity. First nuclear reaction was performed experimentally in 1919 by Rutherford to expose nitrogen to alpha particle. Right? That's a nitrogen. You send alpha particle to nitrogen nucleus from radioactive element radium. producing oxygen. So the end product is oxygen and proton. Right? There's a nuclear formula that you need to know how to write. There's nitrogen, helium, oxygen, proton. Okay, you can see the helium, which is there, carbon, and oxygen. Sorry, carbon is here, oxygen is here. You can see they have high binding energy. Right? But energy release in the reaction is very small in nuclear reaction. So for those nuclear reaction in this part there, energy release is very small. Right? We'll see more detail later on. However, because nuclei are positively charged and repel each other, it was found difficult to bring them close together to react with each other. Right? Remember, the nucleus is positively charged. So to bring one nucleus to another, you have to overcome the repulsive force between them. So you have to provide energy for the nucleus to be pushed together. The discovery of neutron in 1932 helped overcome this problem. Being uncharged and heavy, right? Neutron slightly heavier than proton, uncharged. On the atomic scale, neutron has a high energy even when moving slowly and is a good initiating nuclear reaction. By 1939, many nuclear reactions has been studied, but none seem feasible as energy source. Although energy may be released in the reaction, right, that's a nuclear reaction, more energy was expended in producing particles able to initiate reaction that could be recovered from it. Right? So what's the point? If you have to put more energy in, you're wasting money. So that's why people are not interested in nuclear reaction. Moreover, only a small fraction of the reagent particles could react as desired, and any product particles would have little chance of interacting again. Remember, they are very small. So there's the product is produced. So there's very little chance that bombardment would produce new particle. Right? So the situation is like if I can get a product near my house $10 rather than get a product at KL which is $8 and have to pay bus fare and traveling expenses $4. What's the point? You might as well get it nearby, right? So that's why nuclear reaction not of interest. Question: in nuclear reaction, state the quantities that are conserved. Okay, you should be able to do that. There's your AS work. Got 10 more minutes. Yep. In nuclear
Okay.
reaction, state the quantities that are conserved. Can remember? Linear momentum, charge, energy and mass number. Okay, memorize that. Nuclear equation. Specific nuclear reaction can be written down in a manner similar to chemical reaction equation. Right? That is a short form. Right? That's your chemical, that's your nuclear equation. Okay, we follow from chemistry, reactants, the beginning product, the end product. Right? This is the product, that's the reactants. A is a target nuclei or nucleus. Right? This one is the incident particle, the alpha proton that we send to the nucleus. And this is the final nuclide, the product that's produced. And this is given out. Emitter particle. Right? This is incident particle. particle is the emitter particle. Nuclear reaction. Nuclear reaction is a process where the structure of the nucleus is changed by interaction with nuclei or neutrons. A different element is created. This is an example. You send a neutron to a uranium. Neutron enter and break up into two, produces another neutron. Right? These two are different elements from the uranium. Or fusion, right? Deuterium and tritium, force them together, they produce helium and neutron, and then energy release. Right? So both process produce energy. Okay, mass of A, mass of incident particle, mass of nucleus, mass of nucleus B, mass of emitted particle B, energy release, right? Or binding energy lah. Q value is a measure of the energy released or absorbed in the reaction. So it's defined as total mass of reactants minus total mass of product, right? That's a change in mass times C squared. Okay, or in symbol form lah. Total mass of reactants minus total mass of product, and then the whole thing by multiplied by C squared lah, if you work with mass. If you work with binding energy, right? Binding energy of product minus total binding energy of reactants. Right? That's the difference. Okay, remember that. Memorize that. Binding energy of product minus binding energy of reactants. I won't derive for you lah. Right? Just summarize for you. Total mass of reactants and total mass of product. Exothermic follow chemistry. Reaction energy is released. Exothermic means energy is released. Total mass of reactants is greater than total mass of product. That means this is positive lah. Endothermic reaction, energy is absorbed in the reaction. That means this one, the Q value is negative lah. In this case, the total mass of product is greater than the total mass of reactants. Okay, we won't bother about all these. We still got less than 4 minutes. Okay, that is carry on. Okay, we won't bother about all this. It's just a review of what we have done. Energy for nuclear reaction. Right? This is a neutron. This is uranium. Right? In nuclear reaction, the nucleus becomes rearranged. Right? Different nucleus, different nucleus. Total energy including before and including mass. Total energy including mass before the change because must be equal to total energy including mass after the change. Right? total mass and energy. Total mass and energy must be the same. But this is a review of your AS work. Right? Conservation of nucleon number. You add up these two must be equal to C plus D. Conservation of charge. Right? This is a charge. N plus P is Q plus R. Energy in nuclear reaction. Okay, let's look at specific. If the change causes kinetic energy to be produced, then the kinetic energy of product produced equals to total mass before minus total mass after times C squared. Right? There's a change in mass times C squared. To calculate the energy released or required in nuclear reaction of any kind, we simply add all the masses before and after. Find the mass difference, total mass before, total mass minus total mass after. Then we can convert to mega electron volt. Right? Consider nuclear collision when an alpha particle collides with, right? You should be able to write this equation. Right? Alpha sent in to collide with nitrogen gas, produce oxygen and a proton. Okay, example. There's your reactants, helium and nitrogen, or alpha and nitrogen gas. Add them up. Okay, that's the initial mass, total mass, and then the total mass finally. So mass different. This one, subtract that, we get a negative sign now. And then we use one atomic mass unit is 931 mega electron volt. And 931, right? Mega electron volt. In this case, the mass after reaction is greater than the mass before. Right? This one is greater than that. So what does it mean? Alpha must have adequate kinetic energy for the reaction to take place. That means the reaction will not take place unless you give this energy to alpha for the reaction to take place. Okay, any comment? We got less than 1 minute. Anytime we will shut off already.
Okay.